Thank you everybody for being here. This is our third session of the workshop, Philosophical Issues of Quantum Mechanics. We are really happy to have today Carl Scheffer giving the first talk. He's from Barcelona, from Logos. And Carl, you will have 35 minutes. When you have spoken for 30 minutes, then I'm gonna tell you, so you have 5 remaining. And then we are going to move to 20 minutes of Q&A. So 25 minutes of Q&A. So thank you very much for joining the workshop, and the floor is yours.
Good, thank you. It's a pleasure to be here. And I already said I really enjoyed Olympia's talk. I should have said I enjoyed all the talks that I saw last week. And I'm very impressed with the high level of discussion of quantum mechanics at this conference. I feel bad because I'm not really a philosopher of quantum mechanics, as you'll see, but I can talk a little bit about the things that I think I understand, and that's what I'm going to do now. So the title of the talk is Quantum Non-Locality and Realism, Scientific and Metaphysical. And let's see, compared to the abstract, the emphasis of what we'll be talking about, what I'll be saying today is a little bit shifted. I'm going to spend less time on scientific realism, but I will introduce the form of scientific realism that I defend. It's called TSR for reasons that I'll explain. And I think that some people in the audience may have read a paper where I introduced this. So I'll go over it relatively quickly. And here I just want to note that an assumption, I think, behind my form of scientific realism and really anybody's is also metaphysical realism. Scientific theories are aiming to describe correctly to us the world outside us, which exists and has its features independent of what we may think about it or what we may say. That's metaphysical realism, and it's a kind of a presupposition, but it gets called into question in various ways because of the weirdness of quantum mechanics. So very briefly then, I will explain why I think quantum theories, or fundamental physics today in general, has to be excluded from the domain of scientific realism, which is just makes my form of scientific realism really peculiar and different from what most people who defend scientific realism are trying to do. But I think there's good reasons to do it. And then I think probably most of the time I'll be talking about what the EPR Bell entanglement phenomena and the apparent non-locality of those phenomena, what impact these things may have on issues of whether we should reject scientific realism or metaphysical realism. So that's the plan. Now, the form of realism I defend can be grouped into the kinds that are called selective scientific realism, SSR. And here we have a few prominent promoters who also happen to be friends of mine, of kinds of scientific, selective scientific realism. So if scientific realism says that we should believe in the approximate truth of theories and that they tell us accurate things about the world, well, selective scientific realism takes a step back and says, well, not every theory, not every part of every theory, we have to be objective. And that's a very reasonable response that was taken after the 1970s, I'd say, given the troubled history of trying to defend scientific realism. And of course, prominent in that troubled history is the famous pessimistic induction paper by Larry Loudon, looking at the history of science. So it's especially trouble with the history of science that has led many of these people to go and become selective scientific realists. So the prominent varieties that people discuss in philosophy of science include entity realism, which is the oldest one in this list, from Ian Hacking, for example. Structural realism, for example, John Worrell's version came out in 1989. Stathis Psillos later came up with his own kind of selective scientific realism, and Anjan Chakravarti disagreed with all of them and proposed something he calls semi-realism. And there are other people defending things which I could name. And I take mine to be the most recent entry into this field, as far as I know. So one of the big things that I took myself to learn from the first couple of decades of my career as a philosopher of science was that scientific realists get into real trouble when they try to extend their account of what we have a right to believe because of scientific realism back into the earlier history of science, pre-20th century, basically. John Worrell tries to tell us that no, in the great theories of the 18th century and 19th century, there are structural things that we learned, which we have maintained since then, and that's the kind of truth that realism gives us. But they get into big kinds of problems with historical cases. So, for example, the early atomic theories, phlogiston theory, 19th century electromagnetic theory, to my mind, they all demonstrate that predictive success, well, some at least, predictive success can come in a very early stage of science without a realist stance yet being warranted to the theories or to the entities of the theories. So I came to think that scientific method, if there is such a thing, may be guaranteed to lead us to the truth, but only if nature is kind to us in the first place. And secondly, it's not necessarily going to do it quickly. But nevertheless, I feel the pull of scientific realism like many philosophers do. And it seems to me that the early 20th century marks an epistemic dividing line in many sciences. By early, I mean first half of the 20th century, because in different sciences, the qualitative leap that I'm talking about may have happened at an earlier or later point in the last century. One thing that happened in the 20th century is that our technology grew by leaps and bounds very rapidly, and that gave us many more what I call epistemic handles on things in the world. And secondly, the pieces from different areas of science, chemistry, biology, parts of physics, geology, astronomy, and so forth, the pieces started to fit together and come together nicely into what looked more and more like a coherent worldview, rather than separate islands of theorizing that were kind of disconnected to each other, which would have been the case in the 18th century. Now, scientific realism, I think, kicks in when doubting the theory that you're looking at or the part of science that you're looking at simply becomes crazy. So if we consider other branches of science outside of physics, which are part of what prompts us to be tempted to be scientific realists, we think of geology, biology, parts of biology anyway, the evolutionary synthesis, cell biology, and so forth. Good parts of chemistry, material sciences of the 20th century, electrical and electronic engineering, and so forth. Well, the facts that were discovered in these fields are typically known by multiple routes. We don't just have sort of one experiment or one phenomenon that leads us to postulate those facts. We've got lots of different ways of verifying and getting at them. And the branches in these sciences interconnect with each other in complex ways and form what Quine would call in the 20th century a web of knowledge. So therefore, in the 20th century, what happened is we started to have so many more epistemic handles on most of the core contents of lots of areas of the sciences. And the interdependence, interconnectedness of the sciences entailed that if we want to suppose some core parts of these theories seriously wrong, it would require then positing a chain reaction of further beliefs that we have to jettison and rework and replace with something else. So there would be a kind of a cascade effect that makes it really impossible anymore to imagine how you could do that. I mean, if you try to think, what would we have to do if we decided, actually, no, there are no such thing as chemical elements, or there are no such thing as atoms, or even no such thing as electrons. And then you start to think about all the roles that these items play in the sciences and what it would take to reconfigure the sciences to not have this built in. Then my key claim is that the only kind of worked out consistent hypothetical scenario that you could come up with to accommodate rejecting some of these core parts of science will essentially amount to radical skeptical scenarios. Something like Descartes' evil deceiver or Putnam's brain in a vat type scenarios. The Matrix, variants on a theme. And these type of scenarios we can and should dismiss when we're doing philosophy of science and talking about the debate between realism and anti-realism. Yes, if you're an epistemologist, fine, think about that, take that seriously, but that's not our job as a philosopher of science. So we're left with basically nothing that we can put forward as something that could plausibly count as a scenario where some of these core parts of science could turn out to be false. And so that's my selective form of realism, which I dubbed in a kind of a half a joke, tautological scientific realism, which says we have good reason to believe in the truth of those parts of current science which are such that we cannot imagine a scenario in which they're seriously false, without that scenario turning into a radical epistemic skeptical scenario. And it's called tautological because basically one way to sum it up would be believe in things that you can't see a way to not believe in, or something like that. It comes close to being a tautology. Now, I think that this way of thinking about scientific realism actually captures the correct core of the intuition that so many of us feel, which Putnam tried to capture with his no miracles argument. Okay, I won't take time to say what that argument was, but most of you have probably heard of it. The second thing I want to emphasize about TSR is that it does not function by any kind of inference to the best explanation. I don't endorse inference to the best explanation, and my form of realism doesn't depend on it, and I basically concede to Bas van Fraassen that his criticisms are right. Okay, so this is another way in which I diverge from most realists out there. I think that inference to the best explanation doesn't really play a role in why you should be a scientific realist. Okay, so it's a selective form of realism because not every bit of science, even contemporary science, gets included, and certainly none of the pre-20th century sciences have to be put into the domain. And especially because we exclude fundamental physics. Okay. It's also not the case that what you're endorsing is every detail of the theories that we currently accept, even if they're outside of fundamental physics. Rather, if I wanted to really give you a clear statement of what it is that TSR urges you to be realist about, then we would have to make some very carefully formulated statements with some hedges and approximation and talk and things like that. But nonetheless, it wouldn't be trivial by any means. So that's the the way it looks. And of course, every variant of scientific realism has always insisted that you have to, talk about approximate truth or existence of something very much sharing the properties of what our theory says and so forth. So this is in common with other forms of realism. Look at the time. Okay. So, but why does physics get excluded? Well, in a conference like this, I don't have to say that much. You're all so aware of the features of quantum physics. And by quantum physics, I don't just mean non-relativistic quantum mechanics, although that's what philosophers spend most of their time talking about. But that quantum theories and the whole quantum framework in general is problematic. In the first place, we have the measurement problem. Now, of course, many respectable people tackle that problem and offer some version of quantum mechanics in which the measurement problem is resolved, but that's by no means universal, and none of these theories has universal acceptance. So if we think about the versions of quantum mechanics that, as it were, tell a very clear ontological story about the world, the usual three that people name are GRW, Bohmian mechanics, or many worlds interpretation. You can dispute whether any of these really give a clear picture if you want, and I'm not interested in defending any of these. But the point is, in the domain of classical non-relativistic quantum phenomena, these three are held to be empirically equivalent. And therefore, you've got the problem of underdetermination. Which one do I believe in? If I were going to urge you to be a scientific realist about quantum theories, well, which one? Which interpretation? Which version of it? And then there are many alternative approaches to quantum mechanics that leave it as a mere recipe. That basically say, well, quantum mechanics isn't describing the world out there for you. It's telling you how to make good predictions for your experiments, and that's fine. But then that's instrumentalism, not scientific realism. So that's, again, excluding quantum physics from the domain of realism. And the similar underdetermination worries, or maybe even a new one, afflicts quantum field theories, in my opinion. And one thing I would mention here is the lack of consensus on whether we should even say that there exist particles or not, or just really, when push comes to shove and people say, what do you really think exists? Just talk about fields, or do we still have particles in some sense? And then the measurement problem exists also in quantum field theories. And then there is the conflict between quantum theories as they stand and general relativity, which is yet to be resolved. And of course, I'm not saying that we should believe general relativity to be true, but we still have something that is extraordinarily empirically successful here, and it is in prima facie tension with our quantum theories. So we have all these reasons to exclude quantum theories from the domain of realism. And it's not an exaggeration to say almost all philosophers of physics expect some future major revolutions, and many physicists do too. So when you're in that kind of situation, you're just not in a position to say, we can believe that this is a true depiction of the world. Okay. Now, quantum mechanics, quantum physics in general, may seem to challenge metaphysical realism itself, not just scientific realism. We'll see more about that very shortly. So quantum physics is kind of a double threat, both a threat for scientific realism if it's not cautious and selective, and a threat perhaps to metaphysical realism. So it's a powerful thing. But now, I think that the most plausible way in which those threats come up are having to do with the measurement problem, the lack of a clear ontology, and the problem of the dimensionality of Hilbert space versus four-dimensional space-time, and things like that. But when I was an early career philosopher, I certainly wouldn't have thought that the EPR non-locality gave any particular boost to realism, either metaphysical, anti-realism, either metaphysical anti-realism or scientific. So we do have this apparent non-locality of things that happen with entangled quantum systems, like the EPR-Bohm spin systems, entangled photons, and so forth. But if you'd asked me 20 years ago, does that give any new support to anti-realism? I would have said, nah, it's a non-problem. Now, Einstein, Podolsky, and Rosen thought that the solution to their puzzle was obvious. Particles do have definite properties before they're measured. It's just that quantum mechanics fails to describe them and reflect them, so QM is incomplete, but we don't have to think about any kind of fuzziness in the world or something that threatens metaphysical realism. Now, in 64, as we all know, John Bell showed that in any local theory of the sort that Einstein, Podolsky, and Rosen assumed must be possible, there's an upper bound to the correlations that we can find when measuring pairs of particles at different angle settings in the EPRB setup. The usual thing with Alice and Bob. Does everybody, is everybody familiar? I think that everybody here is familiar with the EPR and entanglement things, so I shouldn't spend any time talking about it. Good. Okay, so this is all well-known stuff. I learned it in the middle 1980s, and I took it as, well, that's nice, but it's not a big surprise. I mean, standard quantum mechanics, textbook quantum mechanics, is an overtly non-local theory. I mean, you can just see it in the way the wave functions spread out and then they collapse instantaneously by the standard interpretation. So no big deal. Of course, experiments back quantum mechanics as predictions. And I just would have said 20 years ago, so, okay, yeah, the obvious conclusion, nature is non-local. Or to put it a different way, the true physical theory of entangled particles is a non-local theory, whatever that may be. But we get from that no insight into exactly how nature is non-local. There's the quantum mechanical collapse of the standard account, but there's also Bohmian mechanics has a different account, and then Everettians have a different story, and so forth. But to sum up, no non-locality, no problem. That was my attitude for many years, and it came as a kind of a surprise to me in the last, say, 15 years, that this is not the way a lot of physicists feel about this whole issue. And many physicists today seem even ready to abandon metaphysical realism and or scientific realism if that's the price they have to pay to keep non-locality. So here's an interesting flowchart. Now, this is from a 1979 Scientific American article by Bernard Despagnat. And he gives this nice article discussing the whole EPR, the EPR argument, the EPR Bell experimental setup, what seems to happen. And then he directs the reader's attention to the three key assumptions that go into deriving Bell's predictions for local realistic theories and the Bell inequality. And he says, well, we're going to have to give one of these up. He expresses these three things as realism, induction, and separability, where what I'm calling locality, he called separability. And for Despagnat, it was not a difficult choice. So he says, of the three premises, realism is the most fundamental. Realism can be stated formally as the belief that a mere description of data is not all that should be required of a theory. Even an empirical rule for predicting the patterns of future measurements is not enough. The mind demands something more. Not necessarily determinism. There's nothing intrinsically irrational about randomness, but at least objective explanations of observed regularities, or in other words, causes. Underlying this demand is the intuitive notion that the world outside the self is real and has at least some properties that exist independently of human consciousness. When all the consequences of abandoning realism are considered, however, it's too great a renunciation to have much appeal. So I won't finish reading this quote, but for D'Espagnat, and I think for many in the 70s and 80s, it was obvious that, well, okay, you just accept the conclusion that nature is non-local. So here's the physicists, and I think philosophers or physicists' view of quantum non-locality in the 1970s and 80s. Ah, that's interesting. Like looking at a Jackson Pollock painting. And here's the physicists, many physicists' view of quantum non-locality in the 2010s and up to now. And I discovered this. I was not a philosopher of quantum mechanics most of the time in my career. I really am not one. And it was a surprise to me to find this out. And it makes me wonder why. And I'd like to pause here and let someone with more experience in the field, and someone who's been around a long time like Olympia or any of you who know, if you can tell me just in 1 minute, why was there this incredible change that so many physicists now will do almost anything to avoid admitting that nature is non-local?
May I say something? I'm not too old to know what physicists in the 80s thought, so I cannot comment on that. But I can have some intuition of why nowadays they think that there's a problem. I think that the biggest issue is that they are convinced that non-locality is incompatible with relativity, which I think it's a false belief. But I think that that's what drives most physicists into thinking that there's something really dangerous with non-locality. That's my intuition.
That's what they say. A lot of them say. If you ask them, why are you so fixed on retaining locality? That's what they'll say. But notice that the importance of locality for relativity was just as clear in the 1960s and 70s and 80s as it is today. But it didn't
I agree. That does not explain the shift. I fully agree.
Yeah, and so there's been a marked change in the sociology of physicists' reactions to this, which I just don't know how to explain. I have a hypothesis, which is a little unkind. I mean, don't take this in a bad way, because I'm Tim Maudlin, but he has spent such really hammered on physicists who are not ready to accept non-locality so hard and so abrasively, that I think he may have actually provoked a backlash single-handedly, which would be remarkable for a philosopher. I'm not sure. So,
Can I say something?
I'm not sure many physicists have even heard about the team. I mean, they don't even know that he exists. So that would be giving him too much credit. I don't know. Maybe you're right.
Yeah. So Olympia.
I feel I can. It's an idea. I never thought about that, but perhaps the development of quantum information drove physicists to a revival of instrumentalism. So what I measure is local, and so they don't want to hear about little bit metaphysical ideas. Perhaps it's a just guess. I don't know.
Yeah, I mean, I'm sure there are many reasons for different people.
Could I say something? Hi. I would like to tell you about quickly about two theories of general relativity alternatives that are not local. They were published last year, I believe, or last year, from the Sergio Mendoza and Barrientos, and they're trying to explain problems of dark matter and dark energy with non-local models of general relativity. And they're starting to have very good results, I believe.
Yeah. That's cool, and that would not cause me any reason to not give me any reason not to take these theories seriously. So thanks. Okay, well let's move on then. Here are some of the ways that physicists themselves present why they don't have to buy non-locality even after we have all these EPR experiments. And the usual thing they say is, well, Bell's theorem is based on a mistake, or it's mistaken, or the derivation fails because, for example, he's presupposed determinism, but of course quantum mechanics rejects determinism. Or others say he presupposed that systems possess hidden values for measurables like spin before measurement, but QM of course denies this. And others will say, well, he proposed counterfactual definiteness, but this violates the principle of complementarity in quantum mechanics. And finally, his derivation presupposes the axioms of classical probability theory, but in quantum mechanics, we learn we have to use quantum probability. It has different axioms. And once we do that, we see there's no problem. We can't derive the Bell inequality anymore. So I've heard all of these things, either at conferences or stated in published papers by physicists. And they're all wrong. All of these things I think are wrong. Then there are the physicists, very few, but like Tuft, who say that the parameter independence assumption that Bell made may be false in our world, which is the assumption that the choice of the direction in which to make a measurement on each side is not statistically independent of the prepossessed values of spin of the particles. And that's considered conspiratorial. And finally, some physicists really just do get rid of metaphysical realism. They say, well, or no, this one here is not necessarily rejecting metaphysical realism. Here, you can say Bell's derivation presupposes definite outcomes of measurements, but QM teaches us there are no such things. And here I have in mind the Everettian, who says, well, every experiment has all the possible outcomes. Okay, because time is running short, I won't give you this quote from Tim Maudlin on the way that misunderstandings of Bell's results are propagated. I can come back if anyone wants to see it later.
We have 10 minutes left, so.
How many minutes?
10.
10? Well, then I can do it, I think. So Tim, in a paper published about 10 years ago, said, there's a variegated tradition for misreporting Bell's result, so common that it deserves a name. The fallacy of the unnecessary adjective. This fallacy consists of adding an extra adjective when stating the result, yielding no X theory can make the predictions, that is the quantum correlations, for the results of experiments carried out very far apart. Common fillings for X, as Blaylock points out, have been deterministic or hidden variables or realistic. So giving us claims such as Bell proved that no deterministic theory can make the predictions, or Bell proved that no local hidden variables theory can make the predictions, and so on. The fallacy of the unnecessary adjective is not a strictly logical fallacy. Bell did prove that no local deterministic theory, no local hidden variables theory, and no realistic theory can make the predictions because he proved that no local theory can make the predictions. You see the point, I hope. Local is doing all the work here, is what Maudlin is saying. But the addition of the unnecessary adjective yields a highly misleading result. For example, Bell also proved that no local theory written in English can make the predictions, but we should not therefore conclude that writing it in French would change matters. When an unnecessary adjective is added, it suggests that locality can be retained if only determinism or hidden variables or realism or whatever is jettisoned. At this point, many authors have been tempted to conclude, to draw the conclusion that Bell merely proved that we ought to abandon any search for determinism, hidden variables, or realism. But Bell showed that if the predictions are accurate, we ought to abandon any search for a local theory. So that's what Tim has been crusading in much of his career to get people to accept, and they are not accepting it, definitely. So here's one thing I learned from Tim Maudlin, which is that that there's local determinism of the results in these experiments, or local hidden variables being revealed by the measurements, as it were, is not an assumption of the argument. It's an intermediate conclusion. And this itself, another way of putting it would be predetermined outcomes, or predetermined values of measurements, is a conclusion that comes from three premises. First, locality. Second, experiments have definite outcomes. They have outcomes. And the perfect correlations, or anti-correlations when we're talking about spin. Just these three things are enough to get you the predetermination of the outcomes, at least with super high probability. And I say super high probability because, logically speaking, you could simply say, no. It's just like a bunch of people flipping coins on each side, and it just so happens that whenever the polarizers are aligned in the same direction, the coin flips happen to land opposite, but there's no explanation. It's just random. So somebody could logically maintain that, but then of course, the probability of that event would be astronomically small, so nobody actually says anything that bad. So we get this part of the argument as an intermediate conclusion from these three premises. And now I would make the flowchart differently from D'Espagnat, and I would say, here's what Bell's theorem shows us. You have to choose your poison. Start with these three premises: the local determinism of the outcomes that we just talked about on the last slide. No conspiracy, that is independence of the settings of the measurement devices from the prepossessed properties of the particles, and locality. These three are sufficient to derive the Bell inequality. You do the experimental tests that violate Bell inequality, so you know not Bell inequality. Nature violates it. So now choose one, please, to reject. This one, or this one, or this one. And so, as I said, you can find ways to do it like with superdeterminism, if you want. That's not attractive to most physicists or philosophers. Or you can reject locality. This one, if you want to reject this one, then you have to go back and tell me which one of these you're giving up, because these three basically entailed this premise. So again, you could give up locality, or you could give up that experiments have definite outcomes. And not just Everettians, but some other physicists do this. Or you give up, well, you can't give up perfect correlations. That's just an empirical result. So there's really very little wiggle room, the way I see it. You give up, you see what Bell's theorem teaches you, and I basically agree with Tim. You see you have to give up locality. Now, physicists don't do that. So what do? Well, many of them indulge in metaphysical anti-realisms of certain sorts. And one thing that was right about D'Espagnat, his presentation, is that it's true. You can avoid Bell's conclusion if you give up metaphysical realism in various ways. So cubism basically turns solipsistic. So there's nothing to talk about except your own measurement results, which are obviously going to be local. So there's no scope for non-locality. There's various different kinds of Bohrian and neo-Bohrian ways of making reality not, as it were, independent of us, but observer-dependent or relative to us, relational or something like that. or you can embrace conspiracy in the form of superdeterminism like Tuft, or unknowingly or implicitly, and the consistent histories interpretation of Griffiths does this. Or in the form of retrocausation. If you have a retrocausal theory, so that you're setting your measurement outcome, your measurement directions somehow influences the past, that's a kind of equivalent way of getting you the lack of independence. And so I file it under conspiracy, although it may be more respectable in some ways. And finally, physicists try to say something about quantum probability, as I mentioned. And when a good, honest physicist in a debate with me on these issues gets cornered, starts to feel cornered about what explains the correlations between these particles, this is what tends to come out. It's a mystery, but it's just the way nature is. And that's not an explanation of how the correlations are maintained.
No.
So, or you can go Everettian and simply, I won't discuss this, but arguably there's no problem of non-locality for the Everettians. Okay, so from my perspective, all of these things are much worse than the problem they're trying to solve. Non-locality is much less problematic than these pills that I'm being asked to swallow by a lot of physicists today. I'm almost done. I wanted to make a brief comment on this idea that quantum probability saves you. Once you realize that there's this new thing, new probability theory, quantum probability, and it's got different axioms, then the problem goes away. Well, I don't think that's right. Probability can be taken either in a subjective direction, subjective probability, but if you go this route and say, when I talk about probability, I'm talking about subjective degrees of beliefs of agents, well, then you get the Bayesian arguments that put constraints based on rationality, and those just give you the standard probability axioms for free. These are extremely strong arguments in the last 50 years that you get the standard probability axioms out if you start with the notion of rational degree of belief. What about the other side? If you say, no, when I talk about quantum probability, I'm talking about objective probabilities or chances. Well, those are, as long as you believe in a world out there full of experimental results, these objective probabilities are constrained to match the actual frequencies, like the frequencies we get from Bell experiments. And that, in turn, again, basically forces you to have the standard probability axioms, because it's well known that actual frequencies do satisfy the probability axioms. So I don't see any scope really for changing the axioms of probability theory and fixing our problem. What I think happens is that when physicists teach us a new probability framework, they basically tend to be teaching us what kinds of calculations to not do and what kinds of inferences to not draw, so that we avoid making the fatal steps that get us to Bell's inequalities. But that's not a real solution. Okay, and I'll just put here, by way of conclusion, that I'm writing a paper kind of about this this stuff I was talking about at the end with Martin Gomori from Budapest. It's very much in progress, and we're going to look at two of the physicists who strenuously defend locality, Werner and Griffiths, and they've the anti-maudlins in the physics community, and they offer versions of quantum mechanics. They're kind of two different versions of standard Copenhagen theory, but a little bit different. One is called operational quantum mechanics, and the other is the consistent histories approach. And we're going to basically show how what they do is demonstrate that they don't let you derive Bell's inequalities, but Werner is basically rejecting the common cause principle of Reichenbach, which is the same as basically postulating that there are weird coincidences in nature and they just can't be explained. And on the other side, the consistent history side, they basically are making the assumption that's equivalent to conspiracy of the measurement settings and the properties possessed by the particles. So that is a paper I hope will be written in the coming months. And now, thanks for listening, and we can have some discussion.
Thank you, Carl. If you have questions, please write it on the chat, and then we can start with Ronnie, please, and then Elias.
So thank you, Carl. It was a really nice talk. I was wondering, just a clarificatory question. If I understood you correctly, sorry, metaphysical realism can be taken for granted in discussions about scientific realism. And I used to think like that too, but not every day. There's now and then I think about a devil's advocate here. So let me consider the following hypothesis. Can we assume that scientific theories describe approximately correct, in an approximately truth way, the matrix, for instance?
Well, I'm not sure what you mean by the matrix. I mean, if we're living in...
Yeah. Describes correctly a brain of that reality. So denying metaphysical realism, but still assuming scientific realism. Does it make sense?
Not to me. I mean, I think that Putnam came up with a kind of realism he called internal realism, I think, in the 1970s, that tried to do that basically tried to diffuse the skeptical brain in a vat type arguments for the matrix, and let him say that even if we are living in the matrix, what our theories say is true, and there's dogs and cats and all these normal sentences that we utter are still true. For philosophy of language reasons, I don't think that works myself, but it's an idea.
Thank you. Now, Elias, please.
Yes, thanks for the talk, Carl. Very, very interesting. Actually, many things that you said are going to be useful for my talk tomorrow. So thanks for that. I have a quick comment and then a question. The comment is about this the chart this flow chart in which you have a perfect correlation, perfect correlations as one of the hypotheses. Actually, it is true that Bell in his paper in 1964 assumed perfect correlation, but then the inequality derived a few years later by Clauser, Shimony, I don't remember all the names, but the CHSH inequality does not need to assume that. So it's actually nowadays you only need two assumptions, which is locality and settings independence or measurement independence, and that's it. You don't need anything else. So, well, that was just a comment, and I'll talk about that tomorrow. But no, my question has to do with your brand of realism, and my question is the following: when you say that we should be realists about, for example, chemistry or geology or stuff like that, what it's not clear to me is what is it exactly that we should assume that it's true when we say that we're really realists regarding those theories. I don't know if that's if the question is clear.
Yeah, and it's a clear and good question, and I didn't try to really answer it, but one way to think about it is think about your first year college textbooks if you're studying first year geology or first year even physics, actually, before you get to quantum mechanics. When you're studying first year biology, things like that, you get a very coarse-grained description, which isn't strictly accurate, but it has a lot of the core features of the worldview that's kind of in the paradigm of the science that we accept now, whether biology, geology, or whatever. And basically saying that the things that we're teaching our students in those introductory courses are true. And we'll never have to completely throw away and rewrite those books. We may change a lot of the footnotes, but that's the kind of thing that I think is the undoubtable.
But then couldn't we say the same about the quantum mechanics textbooks? I mean, if we leave out the ontology and the difficult questions, isn't the situation exactly the same? There are like some principles there in those books that we are sure that they are true.
Well, I'm not sure what you mean, because what I do think is that the basic quantum ontology that goes into atoms, probably we can take as part of, as not quarantined or excluded from scientific realism, but included. So the existence of protons, neutrons, and electrons, the fact that they bind together to make up atoms, that the number of electrons and the nucleons has a big role to play in the chemical bonds that the atoms can make. All that kind of stuff is okay. But if you talk about quantum theory, I mean, then I'm not sure what you're referring to, but if it's something that starts with Hilbert spaces and wave functions and...
What about, for example, the Born rule?
Oh yeah, no, the Born rule, yes, but that's just that's quantum as a recipe. I mean, that quantum mechanics, it gives you an excellent recipe for calculating the probabilities of experimental outcomes, is definitely on the side of knowledge, but even and realism, but even von Frosten wouldn't have questioned that. That's just the empirical side, I think.
Okay. All right. Yeah, I'll think about it. Thanks.
Thank you. Now, Federico, please.
Thanks for your wonderful talk. You were very clear about many topics, and I'm glad that you mentioned quantum probability, because in many philosophical discussions, many, for example, Bohmians do not even consider the possibility of quantum probabilities. I take that you don't agree with them, but at least you mentioned, and that's a good news. First, I want to ask you the question that you asked in between your talk. It's not that we as physicists are afraid of non-locality. It is just that there is no strong evidence for non-locality. And this is very important. Let me show you this. I'm sending you by the chat a paper, a very recent paper. And you can find a lot of things like that. And as a reviewer and as a researcher, you speak with physicists every day, all the time, and you are looking at models that explain the correlations in a local way and realist way. And it's just, so there are arguments in favor of non-locality and other arguments in favor of locality. And so that's the thing. And now, so this is the real situation. The evidence is not, and the theoretical evidence that we have is not strong enough in favor of non-locality. So I know the works of Tim Maudlin, and I just think it's not enough. The arguments are somehow flawed. They don't consider all the possible models. They don't look at all the literature on the subject. So that's the point. And that's one. And now it comes my question. And I'm interested in your response, because I'd like to see what a philosopher thinks about this. Suppose that you have one of these supposedly non-local events, like for example, Alice measures here and Bob's gets instantaneously influential. So now you said A and B. These are two space-time events, two space-time points that are space-like separated. Due to the fact that they are space-like separated, there exist at least three different reference frames in which one of them, A occurs before B, in the second one, B occurs before A, and in the third one, A occurs simultaneously to B. This is, we have a lot of evidence about this. We know this is true from experiments. You can even give up special relativity, but we know that this is going to happen because of the experiment. So the question is, how can you speak about a non-local effect if you cannot say that A was before B or B was prior to B of simultaneous? There is no objective. So how can you speak about a non-local influence? Because in the violation of Bell inequalities, you cannot use quantum system to signal. You cannot send a signal. So non-locality is not violated. And at the same time, the supposedly non-local effect is ill-defined because there is no time order relation between the events. So what do you have to say about that?
At first, Bell himself proved that you can't use these things to signal, so that's not a surprise. And he still believed that the lesson was that nature is non. So the fact that you can't signal doesn't mean you have no violation of locality, unless by definition that's what you mean by non-locality, in which case you're just using different terminology. But secondly, about the reference frame issue, this is a very good point, and I'm not fond of anything and any model that explains by having an event here somehow be the cause and the change in the values of the thing over there be the effect in the normal sort of like signaling type way, that because of the problem of the reference frames that you pointed out from relativity. So I don't think that that's a very promising way of thinking about it. But you don't need to think about it that way to be talking about non-locality. That's important. Non-locality is just the non-statistical independence of the outcomes here and the outcomes there. That's all it is. It's not a promise that one is the cause of the other, or even that there's anything going in between or anything like that. So what explains it? I don't know, you tell me. But I do know that the evidence of the correlations themselves is prima facie strong evidence for non-locality, dependence of what happens here on what happened over there, or vice versa, or mutual interdependence if you want. And if you want to deny that there is that kind of dependence, you have to give up one of those premises that I isolated for you. So which one do you give up?
Are you asking me?
Yeah.
I really think that it doesn't follow. I mean, as I told you before, if you read, there's not much evidence. I will give up realism, what you call anti-realism. That's the most natural choice. I think that the word is probabilistic and that the probability is objective. And the features of quantum probability are such that they are contextual. And so what you're observing is just contextual behavior. That's a possible answer. I know that you don't like it, but it's not about I like it or not. It's about the evidence that you have in favor of each explanation or not. So the empirical evidence don't show any. I get your point that the form of non-locality that you're speaking is not like a direct violation of relativity, for example. Am I right? So you are not speaking about strict non-locality. It's something different. In physics, we call it Bell locality. It's like Bell separability. Like it's like that. It's a different thing than being a signal or the capability of sending something faster than that. Right. So I get that point, and I tend to agree.
Yeah, but when I use the phrase non-locality, it doesn't imply signals. Or
no, I know. Yeah, I know. And that I tend to agree that there's something going on there, but I don't find enough theoretical or empirical evidence for calling that non-locality in the sense of, I don't know, having a non-local word. It's too strong. Perhaps it's a form of holism, as in the talk of Olympia, where she spoke about that. You could consider, for example, what happens in the Olympia's interpretation, and that's a form of holism, and that might well be. But I'm not sure if calling it non-locality is correct. You know, it's too strong, and it's not justified.
Well, holism is one way to think about it. I mean, that is non-local. It is non-locality. I mean, just because, I mean, holism is one way to be non-local. I mean, if both particles, as it were, are inseparably there on both sides, then you touch one, you've touched both. That's non-locality in the sense that I'm talking about it. So
yeah. Okay, thanks for your answer.
Thank you, Federica and Carl. Olympia, please.
Well, coming back to this point of non-locality, in the more recent reconstructions of Bell's theorem, take into account different assumptions. One, non-superdeterminism, definite outcomes, and non-locality. And non-locality is defined as the conjunction between parameter independence and outcome independence, and all these assumptions are very well defined in probabilistic way. So this is what non-locality is. This is the non-locality we are talking about, the conjunction between parameter independence and outcome independence. That's all. This is one thing, but the other thing is to make the comment that a very recent paper of August of this year presented a new, I don't know if you read it, a new inequality which takes off parameter independence. So it's a strong result since it takes, and well, and the paper shows that quantum mechanics violates that inequality too. So since the assumptions are less, the result is stronger. So I think that I promised you tomorrow to send the reference, because I don't remember now the reference. But I mean, it's even stronger, the idea that there are correlations that cannot explain, not even because what there is. I mean, there are correlations, very strong correlations, and the problem is how to explain that, but the correlations are there. So this is something that we cannot deny. This is.
So I don't know this paper, and I'd like to see it if you can send the reference.
Yes, I will send Maria so she can socialize.
Send it to everybody.
Okay, and I have one thing to make a comment about realism, because I'm very interested in that point. I'm working with part of my group also in philosophy of chemistry, and the problem of make quantum mechanics and molecular chemistry compatible. This is a problem. I mean, I find the problems with metaphysical realism not in the problem of scientific change, I mean in the diachronic issue, but in the synchronic issue. I mean, how to make compatible theories or disciplines that are very close, and perhaps they think that they are talking about the same thing, but they are giving descriptions that are absolutely incompatible. For instance, molecular structure is a concept in chemistry, molecular chemistry, and even in quantum chemistry that have certain asymmetries that cannot be explained from quantum mechanics because the Hamiltonian of the quantum Hamiltonian with Coulombian interactions is symmetric regarding rotations, exchange of particles. So the asymmetric shape of the molecules cannot be explained directly and has to be put by hand with what quantum chemists call configurational Hamiltonians that are Hamiltonians built precisely to explain that. So I mean, realism, I mean, that kind of realism, I think that has problems in this, in that, those places, in those, what do you think about?
So this, my answer to Elias helps here, because really the claim of TSR, of scientific realism, is going to be looking at these sciences like quantum chemistry from a bit of a distance and sketchily, kind of like the way that you would teach it in the first year undergraduate course. It's not going to be making the realist claim about detailed Hamiltonians, whether we put in an asymmetric term by hand or not. That's too nitty-gritty and too entangled with quantum mechanics for it to be the kind of thing we can be sure about. But you know, go a much higher level, that that hydrogen and oxygen bond in certain ways that leads to a characteristic shape, and that this explains some of the properties of water. That kind of statement, made in a careful way, is the kind of statement I would expect to be realist to be pointing out.
Okay, thank you.
It's very interesting. I mean, yes, the details of all these theories can get very messy and controversial, and especially when they entangle with physics. So that's a fact.
Yes. So this is, for this reason, I'm a pluralist realist. I mean, and I defend a pluralist ontology. I mean, an ontological pluralism. I mean, so from a viewpoint, I mean, Kantian rooted ontological pluralism. So, yeah. But it's my point.
Thank you. Thank you, Olympia. Thank you. We have 4 more questions. Let's try to be brief. I will be brief. I have a question regarding the tautological selective realism constraints and the role that conceivability seems to play for it. So if I remember correctly, part of the idea is that one of the things that you might not commit to are the things that you can conceive alternative theories, alternative interpretations to that particular either explanation or prediction of the theory, right? So that's the reason why we are not committed to quantum mechanics, because we have all these alternative interpretations, and that seems that we can still conceive something different about the world, and so we don't have grounds to be realistically committed to some. And so considering that, I have trouble seeing why should conceivability play this important role? Because when you consider the other positions that you have in mind, such as entity realism, what entities are doing is providing grounds that are independent from our mind. But conceivability is purely epistemical and depends on the subject. So, and when you relate conceivability to the tautological character of the standpoint, it seems even more odd to me, because tautologies are so reliable because they depend on the most rigorous theoretical foundations of the logics. And what you are saying here is they are going to be tautological because we cannot imagine something to be different. But that to me looks like a very rare mix, and I would like you to say a bit more, maybe.
Well, maybe I didn't express clearly the tautological part of the theory, which is something like this. If you can't conceive of any way to doubt the truth of some sentence S, then you should not doubt sentence S. That you should not rationally do so, and that I take to be something close to tautological or a direct axiom of rationality. But now there's plenty, I mean, inside the domain of what I would recognize as what scientific realism gives us would be a lot of statements about entities. So, I mean, I think that my my view encompasses the kind of entity realism that Hacking was talking about, and then just wants to add some further theoretical things that are not just statements about entities, but more theoretical statements, just not ones from quantum physics. So entity, the fact that scientists posit an entity and get very confident about it, to me, is not yet enough grounds to believe in it. So I don't see the security of entities the way you do. Take dark matter or dark energy as examples. I remain skeptical about that, even though cosmologists tell me, no, we've completely established that there is this stuff. Okay.
Thank you, Carl. So Pedro, Gerardo, and then Moises, please try to be brief.
Since this is not my area of expertise, I wanted to ask a question, very basic question. Earlier you talked about determinism of hidden variables. What I'm curious about is there a necessary correlation between hidden variables and determinism? Are you making this correlation, or is it determinism of hidden variables? It's just a kind of determinism you're talking about?
So hidden variables, in the sense of just positing some structure out there that quantum mechanics doesn't give us. You could have stochastic or deterministic hidden variables doing some story for you or some work in a new theory. It's just that the particular phenomena we get in the APR bell forces, if you embrace locality, it forces you to say that the results of the measurement were predetermined for every direction. That's the sense of determinism that we're talking about. So insofar as you want to say these antecedently possessed values are the hidden variables, they determine the outcomes. That's all.
Thank you, Carl. Thank you, Pedro. Gerardo, please. You're muted. You're muted.
Yeah, can you hear me now? Okay, so thank you, Carl. I'll try to be quick. I have a question regarding non-locality and the Everett interpretation, okay? Because you mentioned it. The common story goes something like this. It is usually stated that you need to assume that in order to derive the inequalities, you need to assume that Alice's and Bob's results are definite, that you have definite outcomes. And I think that is correct. And the idea is that the many worlds interpretation denies the idea that there are such a thing as definite outcomes. If Alice measures the x spin of her particle, then there is a branch with her seeing the up result and another branch with her seeing the down result. So in this particular sense, there is no definite outcomes, and hence you have blocked the derivation of Bell's inequalities. So here's the thing, because you mentioned that this was a plausible way to respond to Bell's theorem. And my problem is that I do not see how the question of non-locality can be as easily answered in the many worlds interpretation. Because on one hand, there is such a thing as definite outcomes for each branch. And so you would say that in the many worlds interpretation, there is non-locality at the local level of each branch. And if you want to say, no, you have to consider the broad picture that Everettians try to defend. But the problem there is that there is no such a thing as a notion of locality, because locality is something that applies to spatiotemporal things, to things in space, basically. And in this big picture of the Everett branches, there doesn't seem to be a notion like that. So can you say something about how do you think about the many worlds interpretation and what kind of solution can they use in this context?
I'm really not an expert in the many worlds view or how they talk about this, but my understanding is that one thing that they sometimes say, and you can say, and I think Maudlin says this, is if you have the many worlds framework, Bell's theorem is just inapplicable, so forget about it. But that doesn't settle necessarily the question of, is there non-local stuff happening in this interpretation or not? Now, I think that what people like Wallace would say is, so Alice gets a result of a measurement on her side, and therefore she's now in a branch where it's up. If you ask the question, what was Bob's result in that branch? Well, until there's no answer to that. There's no determinate Bob in her branch, as it were, until the result from his measurement action reaches. And so there is only after a period of time that's compatible with relativity does there become a fact about whether in Alice's branch, Bob got down or not. That's the story. Whether it makes sense, I can't tell you, and we'll have to leave it there.
Thank you, Carl. Thank you, Gerardo. Now, the last question, Moisés, please try to be concrete.
Hi, thanks for your interesting talk. So my question is about what I think I understand from your position. It seems to be a sort of similar to entity realism. And then I guess the issue I have with that is that it seems to me it's very strange to me to think what a property of what a physical property will be on your account, for example, that doesn't entail some stronger theory or some form of structural realism. So I guess my intuition here is that, for example, when we observe an instrument and observe the results of measuring some, the results of performing or measuring some experiment, intuitively part of what we are measuring is some property of some object. And the ways in which we conceptualize properties usually involve some sort of mathematical structure or complex structure that we are attributing to that property. So in your view, are properties supposed to be something like something that you only get a handle on by performing, you can only talk about as being a result of some experiments, or in the causal nodes of some interventions or something like that?
If you're talking about properties that quantum particles possess, like spin, momentum, and things like that, I have no account to offer you about what they are, or whether we have the right ontology with that classification. I say it's all up in the air. So that's the point of excluding quantum physics for me. Now, if you ask me about the hardness of diamonds, or the properties of viruses and stuff like that, then I'll want to say something based on the sciences that I find inside scientific realism's claim. But I don't have any view about whether we've got anything even structurally right in quantum mechanics, other than Born's rule.
Right, but just a quick follow-up. So, for example, when you're discussing spin and the fact that it's very robust to experiment, it seems like part of what's robust about spin is also our structural understanding of spin, which obviously different interpretations of quantum mechanics will give a different account of. So I don't see why you would accept the reality of the entity, but not of some of its structural features. Yeah, that's just my last point on that.
Okay, thanks.
Thank you, Carl. Thank you, everybody. Can we please give him one of the nice reactions that Zoom has? Thank you for everything. And let's move to the next one. So let's try to keep it flowing. Gabriel?
Okay, we are ready for Federico. You're already the co-host, so you're ready to share screen. Thank you very much. you've got 20 minutes. Do you want me to tell you when you've got like 5 minutes left?
And you are muted, Federico.
Yeah, you can. Yeah, I'm
Okay.
here. Yeah,
I'll
you
let
can let me know when you think I should
Okay,
finish
perfect.
or something like that.
Go ahead. Thank you, Federico.
So, well, I wish to thank the organizers for allowing me to give this talk in this wonderful conference. I will talk about the Cauchy-Specker theorem. I don't know why this isn't working. Oh, here. Okay, so Cauchy-Specker wondered whether it was possible to find hidden variables for a QM that are similar to those of statistical mechanics. So in a statistical mechanics, you have a macroscopic system that is formed by a lot of, say, particles that can be in different microstates that we will represent here by lambda and are members of the state space omega, which is a hidden state space, and that they are governed by the probability distribution P of lambda in such a way that the mean values of macroscopic observables can be written as a usual integral, a solution mean value in terms of these hidden microstates. So for each macroscopic observable, you have a random variable defined in this hidden space to the real numbers, and in such a way that the lambdas assign values to the different observables. And this is done in such a way that you obtain mean values in the usual, with the usual formula. But it's important to remark that these value assignments satisfy what is called in the literature a Funk condition. I will put an example. Suppose that B and A satisfy a functional relation, such as B is equal to A squared. Then Funk says that the value of B should be the value of A squared. So if A is 2, then B should be 4. This is the most general form for an arbitrary function G. So they want to repeat the trick for quantum mechanics, and they say, is it possible to find a hidden space lambda and some hidden variables in such a way that the mean values given by the Born rule can be written in the usual way with classical probability? They assume that these hidden variables, and this is a very strong assumption indeed, obey the Funk condition. This is the condition for them to be physically meaningful. Otherwise, they show examples of theories which are not and not so reasonable from a physical standpoint. And so they arrive at the conclusion that a necessary condition for these random variables to exist is that there should exist an embedding of the partial algebra of quantum mechanical observables into a commutative one. But then they transform this condition into a simpler one that they can analyze using very simple reasoning. They show that evaluation should give value 0 or 1 to the idempotent elements, to the projection operators that represent observables. And in a given measurement context, you will have this equation here, and it's transformed into these equations for evaluations. So in this paper, they show that if these hidden variables satisfying the full conditions should exist, there should be a global valuation from the lattice of projection operators to the two-valued Boolean algebra in such a way that whenever you have this condition, then you have this other condition here. But of course, this will never happen, and they show it explicitly. They put an example, perhaps very complicated, so I will put a simpler example given by Adam Cabello and collaborators in this very nice paper. They show here a four-dimensional quantum system, and each line, each equation here, each line represents a different measurement context of this single system. Each measurement context has 4 possible outcomes, which are represented by one-dimensional projection operators. And only one of them can be true at the same time. So either you put, if you put value 1 for this one should be 0, 0, 0, 0, 1, 0, 0, and so on. And the idea is to give values to these observables. So these equations for the projection operators transform into these equations for the valuation. But no valuation of this sort can exist because on the right, if you sum everything, you obtain 9 ones, which is an odd number. And on the right, on the left, you have, if you sum everything, you will obtain an even number. So they can never be equal, and there cannot be such evaluation. But so where does the contradiction comes from? Well, the problem is that these measurement contexts are chosen in such a way that this guy here is repeated in the first and in the second line. And this other guy here is repeated in the third and the fourth line, and so on. And I depicted here all the projection operators that are repeated. I put them with the same color. So the fact that you repeat elements in different measurement contexts leads you to the contradiction. So the contradiction comes because you are assuming that the quantum system can be identified among the different contexts. So when you consider the system in this line, you can identify with the system in this line, and the value of this property of the system is the same as this one and has the same value and retains its value when you change context. And this is the same for all the ones that are depicted in red, in green, they are repeated. So, but notice that here, in order to reach a contradiction, some counterfactual reasoning is used. And now let me show you a very simple example, a very silly example that shows you why counterfactual reasoning should be taken carefully. So suppose that, what if Argentina had won the World Cup in 1990? The triggering event was the referee deciding between penalty kick versus not penalty kick in the final match with Germany. So if you go to, this might seem very silly, but if you go to a bar in Argentina, there will be a drunk guy speaking about this very loudly and very worried and extracting all sorts of conclusions about what would have been the political consequence of that different possibility. What if we have won the World Cup in the 1990? Well, the answer is that we can only speculate. And it is ridiculous to pretend that we could extract any certain conclusions about this. And at the same time, one may ask, are we entitled to identify the Argentinians of the alternative and mutually exclusive reality in which we have won the World Cup in the 1990? So this example shows you that we must be very careful when we engage counterfactual reasoning. And we know this, and we use it in our everyday life. We know that in a bar, two people who are drunk can speak about soccer and extract any sort of crazy conclusions about analyzing alternative words, which are not the actual one, and then mix the conclusions and extract all sorts of conclusions. But in general, we are not entitled to identify entities belonging to different words, even if they are completely alike until some decisive event, as for example, winning or losing the final of the word occurs or not. So, of course, there are very concrete and important examples in which you can actually do counterfactual reasoning if you specify carefully the ontological assumption. For example, in classical mechanics, if you have one system, you can perform the measurement N1, and you can also perform N2 or not. These two possibilities give place to alternative words, but they can coexist peacefully. You can identify the particle in this reality and the particle in this reality. They are the same because they are not altered. And you can add as many measurements you want because everything can be unified in a single context in classical mechanics. But in quantum mechanics, the situation is very different because of the existence of mutually exclusive context of measurement. For example, take a four-dimensional system, and you can perform four experiments which are compatible, and this defines one context of measurement. But you can consider other contexts of measurement. Both contexts cannot coexist in the same reality. But notwithstanding, they might share some things in common. Some measurements can be performed in both contexts. And you have, in any quantum system, infinitely many possible contexts to consider. And the interesting thing is that they are intertwined. And this is the reason why you get a violation of the Cohen-Spectral theory, because you identify the value of this observable here among different contexts. But let us study this in the two parties scenario. If you have the blue party deciding to measure A and the red party deciding to measure B, you have context AB, but you might also have context AB prime. So we wonder what is the status of identity for A when considered in the different contexts. In the EPR argument, you have a very similar situation. The red party could decide to measure momentum or position, and then you extract conclusions from both contexts, and then you mix them because you identify the second, the blue party in both contexts. But these contexts belong to alternative realities. They cannot coexist at the same time. And so we wonder if we can identify this quantum system when considered in this context and this quantum system when considered in this other context. Of course, there is no question about a mechanical disturbance because they could be very far away. The reasoning here comes from the other side. It seems, are we entitled to mix conclusions and identify entities from different and alternative realities? But it turns out that the identification of quantum systems is problematic because the symmetrization postulate tells us that there are essentially two big classes of quantum systems, bosons and fermions. They obey very different statistics, and this is expressed in the existence of Bose-Einstein statistics and Fermi-Dirac statistics. And in order to show you why and in which sense quantum systems are utterly indistinguishable or truly indistinguishable, let me show you an experiment. Suppose that the blue party in laboratory A creates a particle or a quantum system, and the red party also creates a particle of the same kind. And then suppose now that they are a sort of Bohmians and they assume that the particles have identities and that they can be labeled. So they call them alpha, the particle of laboratory A is called alpha, and the particle of laboratory B is called beta. And then those particles go through an interaction process. And at the end of the process, one particle goes to A and one particle goes to B. But now the experimenters ask, did alpha return to A and beta return to B, or did they switch? Well, it turns out that according to quantum mechanics, there is no operational way to decide which of the things occur. So it's not possible to decide what happened, if they were switched or not. So we get to a very strange thing, because if quantum systems are artificially identified or labeled, then provided that quantum mechanics is correct, the information would be lost forever after the interaction. Thus, our Bohmian experimenters find a weird form of ontological concealment. There is something in the laws of nature that forbids them to recover the information about labeling. And there is no classical analog of this. No matter how hard you try, you will not be able to do this with billiard balls, because in classical mechanics, there is always, in principle, a way in which you can operationally re-identify the particles. I call this the principle of no re-identification. You can see the discussion here, for example. So this sort of reasoning and experiments and ideas led, for example, Schrödinger to conclude that we are compelled to dismiss the idea that a particle is an individual entity which retains its sameness forever. Quite on the contrary, we are now obliged to assert that the ultimate constituents of matter have no sameness at all. I beg to emphasize this, and I beg you to believe it. It is not a question of our being able to ascertain the identity in some instances and not being able to do so in others. It is beyond a doubt that the question sameness or identity really and truly has no meaning. So Schrödinger was pointing its finger towards an alternative ontology with regards to individuality. And then never forget that indistinguishability is a salient feature of quantum mechanics, and it is an independent postulate. It cannot be derived from other principles. You have to say that they are indistinguishable. And never forget either that indistinguishability is not the same as entanglement. You need something else. With entanglement enough, you don't create real indistinguishability. And it's not just a weird metaphysics that you use during the Sundays, and then when you go to work, you forget about it. No, it's just what the physics knows from many years now. And so it's This is what lies behind the phenomenon of superconductivity. And for example, during the last decades, with the advent of quantum information, people realized that indistinguishability can be used as a resource for quantum information processing. This list is, of course, completely unexhaustive, and it is full of words where indistinguishability is used in different ways by physicists. And these are the right idea. So past its negative denomination, indistinguishability or non-individuality, are concepts that leads to a positive physical principle. It allows physicists to conceive new physics. And it can be used to develop technological devices. It can be considered as a resource in quantum information processing. Thus, why not taking it seriously at the ontological level? Of course, if you don't like what the physicists do, you can always be a Gomian. I mean, that's out of question. You can always have this choice. But here we choose to remain close to physics and explore on the assumption that there are in nature objects which are different solo numero and that cannot be considered individuals, as Schrödinger suggested. We are going to explore the consequences of this assumption. So let's go back to contextuality. ¿Cuánto?
5.
Ah, 5.
5.
Yeah, perfect. Yeah. So let's go back to Cohen-Specker contradiction. We saw that the contradiction was due to the fact that we assumed that this property here retained its value when we moved to a different context. So if we think about, again, about the Cohen-Specker theorem, we can summarize the assumption that leads to the contradiction at the ontological level as it is possible to assign context-independent values to all measurables of a single quantum system. So this must be false because you reach a contradiction. One way of negating is saying that properties cannot have well-defined context-independent values previous to measurement. This is a popular conclusion. Many people, you will find this in textbooks, but what we stress is that there is other reason why this can be false, which is connected with one, which is quantum systems or properties are not identifiable entities, if you remember Schrödinger, and therefore they cannot be identified among the different contexts. That could be, well, the case. So this is discussed in this paper here. You can take a look then. So let us illustrate this in the context of 3 dichotomic random variables. If you assume that in context x, y, and x theta, and so on, the random variable x retains its identity, and then it preserves its values when you change context, then you will find out that this table, you can do it by inspection. You create all possible values, and then you build all possible values of x product t, and then you will arrive to an inequality for the correlations. This is a simple example of a non-contextuality inequality. But then if we go back to quantum theory and consider the property A in context AB and the property A in context AB prime, you have different options. You might say that A is the same, so it retains its identity among the different contexts. Another option is that they are different, as proposed by some people. But what we say is that they are indistinguishable. In the following sense, we consider, instead of A, we consider all possible measurement contexts in which A can exist. And we propose to describe this as a class, a collection of all indistinguishables from us. It's a collection that has a lot of indistinguishable entities. And for that aim, we use quasi-set theory, the one that Tesio talked last time. So in quasi-set theory, you can describe collections of truly indistinguishable objects. Like in the left, I put something like classical set theory, very simple. You can speak about the identity of these objects here, but in quasi-set theory, you don't have the notion of identity. So all the elements are indistinguishable. And this is so strong that you can even use it to reformulate quantum mechanics. For example, in this paper here, we give a formulation of Fock space quantum mechanics using quasi-set theory. So then when you don't identify the random variables among the different contexts, you might end up in this table, which is completely non-classical and violates the non-contextuality inequality. So we have shown that one of the hidden ontological assumptions behind the derivation of the KS contradictions is that it is possible to identify the system and its properties among the different contexts. But quantum systems are not identifiable. And it has important implications in ontological discussions. Because indistinguishability is one of the main features of quantum mechanics, and it has to be taken into account when we try to extract conclusions from experiments and theorems. So you are not obliged to assume it, but you must be careful and always acknowledge whether you are assuming it or not in your derivations. And our considerations lead us to an interesting connection between the notion of indistinguishability and contextuality, because indistinguishability seems to imply contextual behavior. So these are some references that you can check, or you can send me an email to this direction and I can send it to you. And I will repeat an extended version of this talk next Thursday and in Spanish. For if someone doesn't speak English, you can attend to it. So well, thanks for all. That's all.
Thank you, Federico. If anybody has questions, please say it in the chat so we can put some order there. Okay, Pedro first. Go ahead.
Hello. My question deals with the concept of indistinguishability itself. It seems to me that the definition of indistinguishability, or at least it seems to me that indistinguishability itself is not a metaphysical, is an ontological property, but epistemological one. Would you agree with that? Just so I can make a follow-up.
Yeah. Well, you have two options here. Let's go back to experiment, right? You have two options. You can always assume that this quantum system have a sort of hidden identity. What you can know for sure if you read of the experiments is that if there is some kind of distinguishability, it is hidden. Because if you label the particles, you will lose the information forever. So if you're a Bohmian, indistinguishability will be epistemical. But there's another way to put the problem and say, well, no, perhaps it is that they are truly indiscernible objects outside there in the world. And that's another different metaphysical assumption. So you can follow both paths.
Because it seems to me that if you prioritize the epistemic conception of indistinguishability, you would be inverting the order of things, wouldn't you? Like you would be assuming that indiscernibility depends on indistinguishability. You know, it would depend on the ontological would depend on the epistemological. Do you get what I am trying to say?
Well, it depends. As I told you before, you have several options here. What you have is that you have an operational indistinguishability that has no classical analog. That's the important point. So if you go, I mean, perhaps if you don't, I don't know if you're a quantum physicist or not, but if you think about it for a while, you realize that something different is going on here. It's not just that there are two balls and I hid them from you and you don't know. That's what physicists tend to think about this, because this is what it seems to be happening. And of course, you never know. And you can always assume that there is some kind of hidden identity, or perhaps that quantum theory is wrong. And at some point in the future, there will be some technology that allows you to discern the particles and identify them. But the usual way to see this, and the usual way in which you reason about this problem, is that they are utterly indistinguishable. So when you look at Schrödinger, he was going into an ontological direction. He's saying that they are not individuals. And for example, I don't know if you had the opportunity to attend to Olympia's talk last time. Did you? Well, she spoke about an ontology of bundles of properties. And that's interesting because that's an example of non-individual entities. Those are, if you take bundles of properties, they might be individuals or not, but they are not individuals in the sense that you have a kind of substance or subject that with attributes or objects. So it's just bundles of properties. So in her ontology, you have non-individuals also. Of course, here we are speaking of something that can be different. It could be, the point is this, perhaps, and if you don't know quantum mechanics, perhaps this is the shocking part. It's something new. It's a new feature of the world. And this is how, in physics, or what is called the received view, elaborated on the notion of non-individual. Of course, it has to be developed and perfected by metaphysics. But it is ontological. It works at the ontological level. And it is a concept that gives you a working principle.
Can we go ahead to Alessandro's, please? Thank you very much. Very good.
Thank you.
Hi. Hi, Federico. Thanks for your talk. So I have a question. I think there is something I'm not getting, so perhaps you can help me out there. So as far as I understand, the literature about indistinguishable particles is a literature about particles. So the relata of the relation are the particles. So I say, you know, for instance, when we count systems of bosons of fermions, the typical conclusion that is drawn is that bosons and fermions are indistinguishable. So this is a thesis about the particles themselves. Whereas in the case of the Cohen-Specker theorem, if I understood what you were saying, is that what we are identifying across contexts are the properties. So for instance, I want to say that given the non-contextuality constraint, I want to say that the very same property has a given value in two different contexts. And so in this case, what I'm identifying are the properties, not the particles. And so it seems to be a different thing that is going on there. So can you help me out on unraveling that?
Yeah, correct. That's a very good point. You can look at it in the papers because we discussed that in the papers. Here I didn't have time, so I put everything very fast. But the thing is that what is new about what we say, look, until the third part of my talk, everything is old. I mean, it's just standard quantum mechanics. It's the things that you need to know to do physics somehow. But in this part, what we claim is that something that we think is new in the literature, which is that when you move from context to context, you are using a hidden assumption, which is that you are identifying the system among the different contexts. We say that you can do that in classical mechanics and leads to no contradiction, but in quantum theory might be problematic because all the experience and all the things that we know suggest that perhaps quantum systems have a problem with regard to the classical theory of identity. So if you take that into account, you realize that what you are doing is that you are considering the same system in different contexts. And of course, the argument, the reasoning line can be for both. You have to separate between particles and properties. These are different things. So in the papers, we study the conclusions of assuming that particles can be identified or not, and the conclusions that follow from the assumption that properties can be identified or not. I agree, they are different things, and perhaps they are related, because what we argue is that somehow if particles are indiscernible, then properties will be too. But of course,
that doesn't seem to follow in general. I mean,
no. It doesn't. I agree. It doesn't follow in general. Yeah. So I agree. They are different levels, particles and properties, or fields, whatever. I'm not married by the ontology of particles, you know. Even it could be just an ontology of properties. I don't know if you attended to Olympia's talk. Well, it doesn't matter. But you might have, for example, an ontology of properties. And then if you go here, you will find that one of the hypotheses of Koch and Specker is that somehow this property retains its identity in the different contexts, as at least to the point that it retains its value. So we are saying that perhaps what you have when you go here and you go there, you have indiscernible elements, that yet they are not the same. And perhaps that's the reason why they behave in a contextual way. That's what we are saying. So this is, so yeah, you see the point. But I invite you to take a look at the articles. This works as a kind of ontological exploration. We assume an ontology and we see the consequences of this.
Okay, thank you very much, Federico. And we've got one more question from Jonas, please.
Thank you. Thank you, Federico. This is a very short clarificatory question. Could you go back to the slides that you had on the hidden assumption of the Cauchy-Specker is the one that you were, when you were answering to this previous question by Alessandro? Yes. So just to make sure that I understood properly in your comments. So the typical solution is number one, so that properties cannot have well-defined context-independent values previous to measurement. Mm-hmm. And then you say you can question this solution due to indistinguishability. But my question is, if you are not...
No, wait. Can I perhaps I say it again? Because it's not that we question one.
Okay.
We're saying that there are different ways in which KSH can be false. One or two are not antagonists. One may be true, two may be true, and both of them might be true at the same time.
So yes, so my question is this one, whether you are not already using the idea that properties are contextual to advance your proposal. So maybe you are using the Cauchy-Specker to explain what is going on in the Cauchy-Specker with indistinguishability. Because
well, I don't think so. Let us go back to
different. Well, in your drawing, you assume that there are different contexts, and then you say, well, but indistinguishability is compatible with that. So are you not just adding something to the Cauchy-Specker instead of giving an explanation to it?
Let me see if I get your question. What we say is that when you consider the system in this context, and then now you consider the system in this context, Cohen and Specker assume that it is the same system. So you have a lambda that gives values to all the variables. So they assume in their ontology, they assume that there exists a lambda, which is the hidden parameter, that gives values to all the p's. And so this lambda and the system are the same, each line to each line. So what we say is that if you, in order to reach the contradiction, you are using it. Cohen and Specker are using it. You have to use it, because if you don't use it, you are not entitled to say that this guy here should have the same value. Because if, suppose the most extreme form is this. Suppose that this blue guy here is different from this blue guy here. So why should they retain the value? You see the point?
Yes, I see, but anyway, when you explain this in terms of different context, you are already assuming the conclusion of the theorem. And I don't think that this is something that they assume. They take this as a conclusion.
Wait. Do you want me to put the Cohen and Specker paper here?
No.
I don't know.
No. I think that.
But wait. This way of posing, you think that this is not the right way of putting the Cohen and Specker argument?
No, I think this is the right way, of course. I think that the problem is just that when you explain that the blue P in the first line and the blue P in the second line are appearing in different contexts, you are already using the idea that there are different contexts. And that's not part of the hypothesis of Cauchy-Specker. That's a conclusion of their theorem.
No, but in the Cauchy-Specker paper, they acknowledge that you have you have in the Cauchy-Specker paper you have a they have a compatibility relationship. It's very explicit on that. So you have observables that are compatible, and then they prove that when you have a maximal set like this, I mean, the projections must be evaluated to the 0, 1. That's what they conclude. The idempotent elements of the algebra. So those are the contexts. If you want, don't call them contexts. Call them whatever you like. Call them maximal sets of compatible observables. Well, if you assume that the system is the same to the maximal sets of compatible, put them the name you want, but they have a very specific technical meaning that you cannot give up. That's not it's not an ontological thesis. It's just the formal structure of quantum mechanics. But it connects with ontology because you assume that there's a physical system and that those idempotent elements are special properties of that same physical system. I don't know if I'm answering you or understanding you perfectly. Please let me know.
I think maybe we can pick this up later, but thank you very much for the discussion. We have to give a big applause to Federico, and please use your reactions, show him some appreciation. And we can go on with Cruz Davis. You're already enabled to share your screen if you like to. If you're ready.
Sorry, I'm technical issues over here.
No, don't worry. I'll let you know. You've got 20 minutes. I'll let you know when you've got 5 left. Okay.
Okay. Let's see if I can get this. Do you guys have that?
Yes, perfect.
Yes, we can see it. But can you make it closer? So, yeah.
Better?
Thank you. Better.
Okay, so I guess my talk's gonna differ a little bit from the norm here of what we've been discussing. One of the things that I'm generally interested in is what we can take as different consequences from naturalistic theorizing about the ontology of various sciences, and then take that in and see what sort of broad metaphysical consequences that has, like across the board, or in particular with this talk I'm interested in how certain theorizing about the nature of particles has with what sort of consequences that has with higher level ontology, and in particular the nature of composition. So what I'm going to be doing here is I'm going to be assuming that the people who take on a view like Krauss's, where particles are non-individuals, are right, and then just exploring some consequences of that on the nature of composition, or at least some theories of the nature of composition that have been picking up some popularity over the last few decades or so. So yeah, I'm gonna really quickly just go through the stuff on particle, on particle non-individuality. The way I understand this claim is that certain fundamental particles lack determinate identities. That is, there aren't any identity facts or distinctness facts that hold of them or between them. We've seen various motivations for this over the last few days of the workshop. You can motivate this view from quantum statistics and the number of states that you get. If quantum particles, let's take bosons. If bosons had determinate identities, if there are identity and distinctness facts that held between them, then the possible states that we would distribute the probabilities over, the outcomes over, would be more than what we in fact see. And so this is reason to think that the particles themselves don't have identity and distinctness facts that hold about them. So what I'm going to do is say that if this claim about the identities of particles is correct, then we're going to run into certain views of mereology are going to run into some problems, and we're going to have to give that up. In particular, I'm interested in views of composition where they treat composition, the nature of the parthood and composition relation, as something that is at least strongly analogous in very important respects to the relationship of identity. And I'm going to argue that main ways of cashing this out, that view of composition as identity turns out to be wrong. And at the very end, I'll just briefly discuss some what I take to be the most interesting consequence of this. All right, so you know, I know we're at philosophy of physics workshop, so I didn't know how much mereology background everybody had, so I figured I'd do a little quick premiere here on the nature of parthood. Parthood's understood in a broad way. We often think of parthood in ordinary language in terms of what's called proper parthood, which, like, my hand's a proper part of me, but it turns out to be the case that I'm also a part of me on standard mereology. So you get the reflexivity of parthood. Each entity is a part of itself. Parthood's going to be transitive. Here's some important definitions. You can define three of these in terms of each other. Overlapping. So X overlaps Y, just in case X shares a part with Y. Disjointness. So X is disjoint from Y, just in case X does not overlap Y. In other words, X is disjoint from Y, just in case X does not share a part with Y. Proper parthood. Something is a proper part of another, just in case it's a part of that thing, but not identical with it. And then fusion, which I take to mean the same thing as composition, is such that Y fuses the X's just in case each X is a part of Y, and each part of Y overlaps at least one of the X's. So Y is composed of the X's, just as understood as Y fuses the X's. Most views of composition as identity also accept classical mereology, which has the following two axioms. Uniqueness of composition, which says that for any things, those things have at most one fusion. So it's never the case that you have two distinct things that share all the same parts. and then unrestricted composition. So for any things, those things have at least one fusion. So take any arbitrary plurality of objects, and there's going to be something that those objects can pose. Another thing that follows from this is extensionality. No two objects share all and only the same proper parts. Uniqueness and extensionality are going to be the targets of my paper. All right. So a little background on composition as identity. Composition as identity, which I'll just label as CAI, picks out a family of theories that take the composition relation to be at least importantly analogous to identity, if not just the same thing as the identity relationship. So what's the motivation for holding such a view? I mean, that view seems a little bit weird. It looks like it, requires that we think about pluralities and singular objects in a very specific way. I mean, maybe, we're already in the realm of weirdness when we deny that reflexivity of identity universally holds here with non-individuals. But here, consider this following case that comes from Baxter, and this is how Bricker puts it. Someone with a 6-pack of orange juice may reflect on how many items he has when entering a 6 items or less line in the grocery store. He may think he has 1 item or 6, but he would be astonished if the cashier said, "Go to the next line, please. You have 7 items." We ordinarily do not think of a 6-pack as 7 items, the 6 parts plus the 1 whole. Another way to think of this is, imagine if you're going through the checkout line at the grocery store with your 6-pack of beer, and then they charge you for each of the individual cans and then add an extra fee for the whole pack, right? They'd be charging you for 7 items, but it seems like they should either charge you just for 1 or just for 6. Something seems to go wrong. I think you'd look at the clerk and be like, "What the hell, man? What's wrong here? Something went amiss." So the idea that's supposed to motivate composition as identity is this really tight relationship between parts and wholes. We don't want to count both the parts and the wholes. That would involve some sort of double counting. Wholes are nothing over and above their parts. So they don't count as any extra addition to our ontology, or at least the proponent of composition as identity is going to want to say. So proponents of composition as identity think that the only way to really truly explain why you can't double count parts and wholes in this way, and this tight relationship between parts and wholes, and the fact that parts aren't anything over and above the wholes that they compose, is that composition is very, very much, if not exactly the same as the relationship of identity. There's another motivation that I'll just briefly touch on, which comes from certain Humean modal metaphysics. Humeans don't like brute necessities. They don't like any necessities that can't be boiled down to analytic truths or truths about logic. And one of the things that they want to say is that the parthood and composition relation shouldn't be freely recombinable. We can't mix them up and match them in any way that we want. This would lead to absurd conclusions. So for the Humean, what they do is they divide the logical relations in the world from the qualitative ones. And they want to say that the qualitative relationships are ones that can be freely recombined that you can, kind of throw in your bag, mix up and toss out and see however they come out, and you get a new possibility. But the logical features of the world aren't freely recombinable. Having a view where composition is very close to, if not the same as identity, is supposed to prevent this. So it puts composition in the family of logical features of the world, as opposed to being among the qualitative ones. So just like identity isn't freely recombinable, you can't recombine my identity, say, with Moisés's. It's also the case that composition isn't freely recombinable. So there's various strengths of the thesis of composition as identity. As I mentioned, it's a family of views, and the way you divide the views up is how strong you take the relationship to be. So there's strong, moderate, and weak composition as identity. Both the strong and moderate versions of the view have this notion of being the same portion of reality. And what you can kind of think of is imagine you have like a hunk of clay, and you just you could divide it up every which way. You could either leave it undivided or cut it up into bits. The idea is if I cut the clay up into like little different squares, that's the same portion of clay as if I leave it uncarved up. And this is something that both the strong and moderate camp are going to accept. On the strong camp, they take the identity relationship and the composition relationship to literally just be the same thing. The identity relationship can be flanked either by singular terms, plural terms, or a mix. When we have composition, or at least what we should call like proper composition, where you have some plurality of parts composing a singular thing, that's when you've got a plurality on one side of the identity relationship and a singular term on the other. And then you make sense of this by thinking of portions of reality as things that could be either considered plurally or singularly, depending upon what concepts get deployed. So the way that we count is concept relative for strong composition as identity folk. On the moderate view, composition is a species of the identity relationship, just like you would take plural and singular identity to be. What it is it's this relationship that goes in the same family as singular and plural identity, but it can be flanked on one side by plural terms and a singular term on the other side. Weak composition as identity is the view that composition is at least very strongly analogous to, or not at least, but just is very strongly analogous to the identity relationship. And Lewis gives 5 theses, which I'll just go over real quickly, what those end up amounting to. So you've got ontological innocence. If one believes that some object X exists, then one does not gain a commitment to some further object that thing's identical with. The same goes for composition. Automatic existence. If some object X exists, it automatically follows that something identical with it exists. Likewise, if some Y exists, then it automatically follows that something composed of, Y's exist, yes, then it automatically follows that something composed of the Y's exists. Uniqueness. If some Y is identical with X, then anything identical with X is identical with Y. Likewise, if some Y's compose X, then any things that compose X are identical with one of the Y's, and anything identical with X is composed of the Y's. Exhaustive description. If Y is identical with X, then any description of Y is an exhaustive description of X and vice versa. The same goes with parts and wholes. And sameness of location. if y is identical with x, then necessarily if x and y fill the same region, same thing goes for a whole in the plurality of parts that compose it. Okay, so how does the particle non-individuality stuff come in? I mean, so you can see kind of from the beginning, this is going to turn out as false right from the start, the L2 part of the analogy, if particles don't have identities and objects are composed of those particles. So, all right. One of the things that I'm going to suppose is that physical objects are composed entirely of particles. Perhaps one way of getting around this is there's this weird view held by Schaffer that physical objects are just composites of space-time points, but I'm going to just leave that to the side for now. I'm also going to assume that the identity of plurality, the y's, is determined by the identity of each y that is among the y's. So if it's the case that the y's don't equal the z's, then there must either be some y among the y's such that y isn't identical to any z or vice versa. So here's the 5 minutes. Okay, cool. So here's how I take these arguments to go. So what's the case against strong composition as identity? Recall that on this view, composition just literally is the identity relation, but it can be flanked either by plural or singular terms or some mix. So consider a situation where you have three indistinguishable non-individual particles, P1 through P1 through P3. I'm probably doing some violence to the theory by labeling them, but let's just treat the labels as just mere labels and not picking out anything in reality for now. And two composites, X1 and X2. Both X1 and X2 are composed of exactly two particles. Let it be the case that X1 does not equal X2. Now, assume strong composition is identity. It's going to follow that there is some determinate plurality, the y's, that X1 is identical to, and some plurality, the z's, that X2 is identical to. But then the y's don't equal the z's because X1 does not equal X2. Since the plurality, since plural identity is determined by singular identity, this must be due to the fact that some entity among the plurals, the y's or the z's, isn't identical to an entity in the other, or vice versa. But this is going to violate the idea that these particles are non-individuals. Remember that the way that we're understanding non-individuality is that no determinate facts of identity or distinctness hold between them. They're going to be, so because they're indistinguishable, it shouldn't be the case that we can distinguish any one of the three P's from any of the other. All right. So how does this work against moderate and weak composition as identity? So let's just adapt the argument from above. Both moderate and weak composition as identity depend on extensionality, which just says that no distinct objects share all and only the same proper parts. So allow X1 and X2 to not be identical. There's going to have to be some sort of difference in the parts that they have. But if there's a difference in the parts that they have, then this means that there's going to be a difference in the pluralities. And so that compose them. So if there's a difference in the pluralities that compose them, then it's going to be the case that there has to be some entity in the plurality that is not identical in one of the pluralities that isn't identical to an entity in the other pluralities or vice versa. But again, that violates the assumption that particles are non-individuals, or at least these particles are non-individuals. All right. So the rough upshot of this is we need to be able to distinguish any pluralities of particles. And so any sort of view of composition that requires that you have to distinguish non-individual indistinguishable particles is going to fall out as false if we accept this non-individuality interpretation of quantum particles. All right, so here's what I think is the most interesting conclusion. Maybe that's not all, maybe that all seems to just kind of trivially follow. But here's what I think is the important upshot, and it's a metaphysical one. One of the motivations for composition as identity, for holding it, is to get rid of the ontological weight or the ontological burden that it looks like composite objects give us. They're not supposed to come at any sort of extra cost. And minimally, this requires something like extensionality. Now, if we lose that and we don't have this explanation for the ontological innocence of adding composite objects, then are we going to have to say that no, actually higher level objects do add things to our ontology and they are ontologically weighty? I think that that's, if you're like me and you think that the only way out of taking composite objects at higher levels to not be extra additions to your ontology is to accept some sort of view of composition as identity, then having a view where particles are non-individuals seems to undo that explanation, and thus we're going to have to actually add some ontological weight to the higher level entities. And that, I think, is a really interesting result. And that's all I got. Thanks for having me.
Thanks.
All right, so.
Got question. Thank you for the presentation and the great presentation.
Should we move to the questions? Okay, so Carl has a question, then Moisés has a question, and then Alessandro, and we wait for more. Carl, please.
Yeah, thanks. Very interesting. Could you put back on the last page of your handout or your slide?
Let me see if I think there's a way to do this. So, like, I'm only 1 week out of the semester, and I forgot how I did this split screen with the students where I could see people's faces.
We should be grading.
Yeah.
Good, and scroll up just a bit.
Yeah, let me move this out so I can make sure I can see everybody. Cool. All right. So where do you want me to
stop?
Right here?
That's good. That's good.
Yeah.
Yeah. So the argument in 5.2, the argument against strong. No, go back up again. The argument against. Oh no, there we go. Yeah, that's good. That's it. The argument against strong and moderate CAI seems to have as one of the steps, let x1 be not identical to x2.
Yeah.
But if we're thinking of x1 and x2 as composed of a pair of indistinguishable particles of the same type, why should I allow that first step? And then I don't see that you're going to be able to derive any contradiction.
Good. So yeah, that's So think of this as a toy scenario, right? But remember that composition is identity is going to hold globally for objects at any level. And so the thought is, this was supposed to be just kind of a rough sketch, and I agree with you there that that's the fishy move. But take two large-scale objects, like I guess our size, medium dry goods, and the thought is that you're going to have indistinguishable particles involved in composing them as well, and it's still going to you're still going to end up having this be the case. And the thought was that either you're going to have the determinacy of the identity and non-identity at some level trickle down to the non-individual particles, or you're going to have the indeterminacy trickle up to objects of our size, where it looks like they do have determinate identities. And so then you'd get a contradiction that way. Maybe
Thanks.
Did that answer your question?
Yeah. I mean, I'd like to maintain that even if you and I have the same number of particles in our bodies, we're different.
Yeah.
The same number and types of particles were different.
Yeah.
Okay, maybe we can go on with Moisés' question.
Yes. So just to clarify, is your conclusion that we have to either revise the axioms of mereology, so give up, for example, some form of composition as identity, or accept that that there's ontological weight? Because I just wasn't I wasn't completely clear on what were the options that were open, and the impression that I got was that you regarded the possibilities as undesirable in either case. So could you say a little bit more about what you think are the possible alternatives?
This up here, with respect to that?
Yeah.
Yeah. So I mean, one thing you could do is you could say, so like, I think of me as arguing for the following conditional. If the non-individual account of if the non-individual's account of particles is right, then composition as identity in any interpretation is false. Then the claim was that in order to remove the ontological weight of higher level objects, something like composition as identity needs to be the case. Or just composition as identity, one of the forms of it need to be the case. So yeah, either you accept the weightiness of higher level objects, which I'm actually attracted to that view, or maybe you have to opt in for something like mereological nihilism and just deny the existence of the higher level entities. I think that I find that really unattractive. But yeah, it looks like if you've got some sort of non-individuals view, you're going to have to revise some bit of classical mereology that would require us to lose any theory of composition as identity.
Can I ask a quick follow-up? So just help me out also with how strong should the discernibility requirement be here for any of the forms of composition of identity to hold. So what I'm thinking is that we know that the particles are not going to be discernible, qualitatively discernible, but for example, if you had something like weak discernibility, you know that, for example, some object is identical to itself, but so for example, two objects X and Y, they have absolutely no qualities. They agree about all qualities. However, X is identical with X and X is not identical with Y, for example. Wouldn't something like that suffice for some form of composition as identity? And do you lose that when you with the with quantum mechanics? I'm not sure about that.
Yeah, so I think like Saunders wants to say that for fermions, you get weak discernibility, but I'm not going with that sense of non-individuality. I'm going with just the identity facts don't hold.
I got it.
Yeah, and so I'm just taking that on as an assumption. You could reject that assumption, and then it doesn't look like you're going to end up with the same sorts of problems, or same sorts of results, rather.
Cool. Thanks.
Okay, maybe we can go on to Alessandra's question.
Yeah, thank you. That was fun. I have a question about extensionality. In the case of indistinguishable particles, when we define a quasi-set theory for indistinguishable particles, we don't get extensionality. We get something called quasi-extensionality, as far as I remember. Essentially because since the members don't have identity, we cannot identify or distinguish sets based on the identity of the members. And so I was wondering if a similar weakening could be implemented in the case of composition as identity. So the idea is that we don't really have identity here. We only have indistinguishability relations between certain collections of elements. And so if we have our two objects, x1 and x2, at most we can say that they're indistinguishable, and from that we can say that the elements that compose them are indistinguishable, and that is consistent with not claiming that they are distinct or non-distinct.
I see.
So I say, yeah, I don't know if that was clear, but
yes,
I hope so.
Composition is identity. Let's call it composition is indistinguishability or something like that. And
that would be a sort of generalization, because the original theory, as far as I understand, was set up in a sort of like very classical set theoretic view of reality, where everything is an individual, which obviously didn't delve into the complexities of the real physical world. And so just like some people have proposed to generalize set theory to quasi-set theory, and something similar could be done with mereology in this case. And maybe we could avoid getting a contradiction, I mean, a reductio.
Yeah, I think that that's definitely a plausible route to go. I've just started thinking about this, so I haven't dug as deeply into the quasi-set theory stuff as I'd like. But I think that would definitely be the route to take. And it maybe then, that's enough for you to get ontological innocence back too. And it's just that these collections of particles are stand in this indistinguishability relation or whatever is enough for us to say that you have innocence. And that what was the I think it was
you would get unique composition up to indistinguishability,
right?
Probably.
Yeah, and you probably, and then you wouldn't have You'd have to change L2 here as well.
Yeah.
You'd have exhaustive description, sameness of location. And then, yeah, it looks like you'd probably be able to capture ontological innocence as well, or at least motivate something along those same sorts of lines. Cool. I like that.
All right. Just a suggestion.
Yeah, yeah. I'll have to look into it. Thanks for the suggestion.
You're welcome.
Okay, we can go on to Pedro's question.
Hello. My question deals with something you said about bundles and wholes and parts. And, can you go back to that example you said early on about
this one?
Yeah, the six-pack of orange. Couldn't we solve this issue of considering? I'm sorry. One moment. It's my cell phone. Couldn't we solve this problem by saying there are kinds of identities the identities derived by the parts and the identities derived by the whole, like you could reify the whole as abstract, but saying they are only parts and not necessarily wholes when considered. You see what I'm getting at? You could try considering identity as a concrete thing and say there are 6 oranges and I want to pay for 6 oranges. But I could also conceptualize the 6-pack, the entire pack, the whole, as something in itself also, but that does not have consequences to our conception of the nature itself.
What do you mean by consequences about our conception of nature itself?
That wholes are not concrete things, but parts are. You see?
Oh, so the idea is that like the only real things are the
no. The only natural things are parts, but we could reify, make it an object. Take the wholes as being abstract objects, but only distinguish parts as natural. You see?
Yeah. So it would be like the parts are the only. Let me just choose a different word to see if I latched onto what you're saying. The parts are the only physical objects.
Yes, that's what I'm trying to.
And
I would deny compositionality for natural kinds, but I would accept it for abstract objects.
I don't know what to think about that. I want to say that I am just as much a concrete physical object as the things that make me up. And I guess I just kind of take that as a piece of data to theorize with. I'd have to see, maybe the motivation for giving that up would be a case like this. But yeah, I'm not entirely sure what I think about that. There's something that sounds or feels kind of nihilistic about it. Yeah, you're saying that there are these composite things, but it turns out that they're not physical objects.
Yeah, that's what I'm trying to say.
Yeah, and that seems
you could say it's a nihilism insofar that it's only if you do not accept anything that isn't natural, that isn't physical. But if you accept some kinds of abstract objects, I don't see. I think it's just separating kinds of identities, if that makes sense, for different kinds of concepts?
Yeah, no, I mean, so this is an interesting question, and like, so one of the things we're entertaining here is we're entertaining giving up like the universality of identity, that everything has an identity, and that feels like that's pretty close to the center of the Kleinian web, right? And so, you know, part of me wants to say, oh no, I don't like this idea of composite things as abstracta, because that would be weird. But I feel like we've already left the realm of being able to make that sort of objection. So I don't really know how to respond to that.
All right.
But I'll have to think about it. Thank you.
All right, thank you.
Thank you very much. If anybody has any other question, we have maybe 2 minutes. If that's not the case, then we can show some appreciation to the class and so on.
Thanks for having me, guys.
Thanks.
Thank you, Cruz. Thank you, Federico. Thank you, Carl, for your talks today. It has been a great day. So we are hoping to see you all tomorrow for the last day of the workshop. Elias Ocon is going to be our keynote. And then we have Jonas and Raoni talk, and then a Moisés talk at the end. So Cruz, before we leave, can you please type your email address in the chat so people can send you emails? Thank you everybody for joining. Looking forward to see you all tomorrow, and
thank you.
See you soon.
See you.